Good. Now, today we're going to start with some basic elementary concepts that are essential to understanding what is challenging about computational methods, and this will also touch on the source of many of your problems. Now, this is all going to be very elementary and at first trivial, but it's not something you should forget. It's something that should always be in your front of your minds. Now, the other thing I'd like to point out is that really computation, numerical analysis, is really just applied economics. Because economics is the study of scarce resources and how you allocate them to accomplish a particular goal. Well, computation is such a problem. You have scarce resources, hardware, the CPU, how fast can it go, how much can it handle. The other aspect of a computer is the memory. Now, there's three basic kinds of memory. There's cache memory, which lies right next to the CPU, and its transfer rates are very fast. Then you have the general random access memory, RAM. That's pretty good. But then some of you may have noticed that sometimes when your program is demanding a lot of memory, that then certainly if you have a mechanical drive, what happens is it starts making noise. Anyway, and that's because it's starting to use the hard drive, or whatever you call them nowadays, to use it as an extension of RAM. Well, the rule is, of course, if you ever hear that, you just kill the process, because that's very, very slow. So you have to understand those layers of memory in terms of what can be done. Now, the really professional, hardcore computer programmers, they understand that, and they can tweak their programs to allocate memory in an efficient fashion across the cache and the registers and the RAM. But this is not something you should spending time working on. But you need to understand that the speed of things depends on how memory is used. Now, the other scarce resource is software. Now, that means the algorithms. There's not good algorithms for every problem that we run into. We also have various interfaces to the computer, some better than others. The other problem about software is that it's not free. And so there's money comes into play. Now, the other thing that is important, of course, to any economist doing computation is the opportunity cost of human time. Human time will always be an input. Now, opportunity cost varies greatly across economists. Some people have a low cost opportunity cost. They don't have many other things to do with their time that's more valuable, so they can focus on fine-tuning their code. Others have a very high cost, opportunity cost. Think of finance professors who do consulting. Well, those guys want to use methods that use the least amount of their time. So this is just like any production function. There's multiple ways of achieving the output, and you want to use resources in a cost-effective manner. The other scarcity is a human ability, and a macroeconomist named Chari made quite a comment on this about macroeconomics. Abstracting from irrelevant detail in macroeconomic models is essential given scarce computational resources, not to mention the limits of the human mind in absorbing detail. Anyway, so that was his comment. I asked him once whose minds was he thinking of, being limited, and he then realized that this was probably not the most intelligent thing he ever said. But anyway, so this is when, with a lot of the algorithms, you might ask, well, why do you do this as opposed to that? It's because we want to reduce resource use, as well as increase the accuracy of the results, as well as increase reliability. accuracy and reliability is what you want, but also you want to have to do it in a manner that is economical on resources. Now, the big problem with using computers is that it uses computer arithmetic. Now, we're used to doing mathematics where there's an infinite number of integers available, there's an infinite number of rational numbers available, and there's an even bigger infinite number of real numbers available for our analysis. That's not possible for computers because there's only a computer only has a finite number of states. I'm talking, of course, about standard digital computers, von Neumann machines, et cetera. Nothing. I'm not talking anything analog. But the standard computer can only have a finite number of states, which of course means it can only have represent a finite number of numbers. Now, the standard representation of real numbers in computers is, as I express here, you first have a plus or minus sign, and then m is the mantissa, which is an integer, and then a plus or minus sign with an integer, and that's the exponent. Now, typically today, computers have double precision processors. Now, what that means is that the computer uses 64 bits to represent a real number. Now, up until roughly the early 80s, computers were basically single precision machines. They could only, each number had to fit within 32 bits. But in the mid 80s, the standard changed to be double precision, 64 bits. Now, for double precision, the m is 52. No, wait, okay. It's not that, okay. The m is 52 bits. That's what it should say. M is any integer that's representable in 52 bits. But representable, by the way, means in binary arithmetic. And the exponent is any integer which can be represented in 10 bits. And then so that adds up to 62, but then you get the sign bits for these. So that's how you get to 64. Now, what does that mean? Well, it means that you can't represent arbitrary numbers. Basically, the definition of one property is epsilon m is basically the largest number which the computer thinks equals 1 but doesn't. And so epsilon m is roughly about 2 to the minus 52, 10 to the minus 16. What does that mean? That means that if you have some number x, which is within 10 to the minus 16 of 1, the computer can't tell the difference between that 1 plus x and 1. Okay, if x is any small number smaller than 10 to the minus 16, the computer thinks that 1 plus x equals 1. There is basically round off error. And so you cannot expect anything more than 16-digit precision with anything using double precision arithmetic. So that's this quantity, which we call computer epsilon, or the epsilon, it represents the amount of precision that the max amount of precision you can expect from this standard CPU. So like if you want to input some number for the computer to deal with, there's no point in writing down 24 digits or 24, decimal digits, because the last 8 are just tossed away. They can't represent them. So this is what you have to keep in mind, that everything that's done in the computer is done using 16 decimal digits. Now, there's also another number that we like to talk about is machine zero. This is the smallest positive quantity which the computer views as being equal to zero. Now that is about 10 to the negative 308. So if you want to represent something like 10 to the minus 1,000, well, and compare it to zero, your computer can't tell the difference between the two. Now, there is software that will allow you to work in higher precision arithmetic. Sometimes it's actually necessary to go to high precision arithmetic. Many years ago, Carl Schmetters and I were working on a paper which all we had to do was solve linear equations, but we were getting crazy answers. Now, my having an economics PhD means that whatever the answers were, I could come up with some economic story explaining what was going on. But then, of course, we changed examples. I have to come up with a different story. That's not good science. It turns out that the problem was we were just using regular precision arithmetic. And in order to get a stable answer, we had to go to 512 digits, decimal digits. And then to check it, Carl went to 1,000. Now, what software did we use? We used Mathematica. That's one thing Mathematica can do. So sometimes you need the higher precision. Now, by the way, if you ask a numerical analyst about using higher precision arithmetic, they will tell you, no, that you first should just rewrite your code so that it's decent. The standard feeling in numerical analysis is that if you need higher precision, you're just incompetent in writing up your problem. Now, there are a few people who do work in this area of high precision, and that's good, but basically all of numerical analysis almost all numerical analysis is focused on what you can do with 16-digit precision. Now there is software, however, that can allow you to use higher precision that you can access. I know for C and Fortran, for example, there are packages designed to put in higher precision arithmetic in those programs. Mathematica and Maple have it, and I've already built in. I bet the symbolic toolbox in MATLAB has it, but the key thing about going to higher precision arithmetic is that when you go to higher precision arithmetic, the performance drops by an order of magnitude. And that's because the arithmetic isn't being done all in the CPU, but it's being done somewhat in the software, which requires RAM access and manipulations. And so so it's much slower. In Mathematica, what I discovered is that going from 16-digit arithmetic to, let's say, like 20-digit arithmetic, it went 10 times slower. But then actually when I went from 20 to 32 to 64 to 128, the speed did not slow down much. It was actually pretty good. Once there's a hurdle, a fixed cost of getting to high precision. And after that, it's not so bad. Now, arithmetic operations take time. Of course they do. Everything takes time. Now, there's a great variation in how much time things take. Integer addition is the fastest. Addition and multiplication, well, integer addition is the fastest. And so there's a lot of software where basically what's going on down in the belly of the program is a lot of integer arithmetic. Even when you think that it should be doing real stuff, it's doing integers. Now, real addition and multiplication are a bit slower. Addition and multiplication are about the same speed, but division is slower than those. And of course, not too surprising. Division is more complex to do. And then you have your power functions, trigonometric, logarithmic, special functions, and they are, many of them are significantly slower. So now, by the way, the other thing, and we'll talk about more of this later, all that the computer knows how to do is add, subtract, multiply, and divide. That's the only thing the computer can do. Everything else, sine, cosine, exponential, whatever, is really just uses a program buried into the CPU. There's a program that if you ask for sine of x, what that program does is, what the CPU does is execute a program, which is a fixed finite set of steps of addition, multiplication, division. Addition, multiplication, division is the only thing a computer can really do. Now, what's nice for us is that it kind of pretends it can do sine and cosine and other things like that. But the only thing, the only thing it can do is addition, multiplication, division, subtraction. So we'll talk a little bit about how they do that in upcoming lectures. Here's the big problem. When you have only a finite number of possible numbers, a lot of numbers can't be represented very well. For example, 1/3. Now, even in decimal arithmetic, 1/3 is a problem because 1/3 equals 0.3333 for an infinite number of threes. So even if you're doing decimal arithmetic, as we generally do in our life, you still have to do round off because decimal arithmetic would require an infinite number of digits. Now, in decimal arithmetic, 1/10 is easy. It's 0.1. Okay, that's easy. However, in binary arithmetic, 1/10 is an infinite sequence of zeros and ones, which of course has to be cut off somewhere. So there's always the problem of round off error. Now, you might say, well, okay, yeah, round off error, but then how bad can it be? Because after all, we do have 16 decimal digits of precision. Well, it's not that simple because knowing exactly how to deal with this is something that changes drastically across different problems. For example, the exponential function, its definition is as an infinite sum. It's an infinite length polynomial. The exponential function is of infinite length. Now, one way to deal with that is to approximate it with a finite number of initial terms. Which of course, this is like a capital N initial terms. You add that up and that's an approximation to e to the x. Now the question is, how many terms do you need in order to get an approximation to e to the x that is acceptable to you? Notice, by the way, that x to the n divided by n factorial, that's just a lot of addition, multiplication, and division, literally, because x to the n, it's not, that's just an integer power, so it's just a bunch of multiplications. But how big should n be? You don't know. Now, also, in a lot of algorithms, computational algorithms, you have a sequence of numbers that you iterate. You get x1, and you get x2, x3, and then the true answer, what you're trying to find, is the limit of that sequence. But the question is, when should you stop? You can't go on forever. You want to get your PhD in sometime in your lifetime, so you've got to stop these sequences at some time. When is that, and how challenging is that? Now, here's an example of the challenge. You start with 16 digits precision, you do a little arithmetic, and you've lost 6, 7, maybe even 8 digits. Arithmetic you don't have to do much arithmetic and you start losing precision. Now, by the way, doing an example in 16 digits is ugly. There were a series of papers I wrote in the past where I think my major contribution was basically telling my co-authors that they had to cut 16-digit numbers in the tables down to something that's more readable and understandable, like 3. But so for me, 16 digits, just not, I'm not going to try to even handle it. Now I'm going to give you an example, which I can understand because I'm thinking about in this world where I have 5-digit arithmetic, 5-digit precision. So think about this quadratic equation. X squared minus 26x plus 1 equals 0. Now, what's the solution? Well, you use a quadratic formula. You see that the solution is, or a solution is, 13 minus the square root of 168. Which, by the way, this is now I'm using infinite precision expressions, is 0.0385186. However, if I did this subtraction in 5-digit arithmetic, that would be 13 minus the square root of 168. 5-digit arithmetic, 13 would be 13.000. 5-digit arithmetic, the square root of 168 would be 12.961. The difference is 0.039. Now, how accurate is this? This has only 2-digit accuracy. The truth is 0.0385186. This is the rounding up of this number to just the second significant digit. So already we started with 5, we had 5-digit arithmetic, we did 1 subtraction, and now we're down to 2-digit precision. It is very easy to lose digits and precision rapidly. Now, here's a little case of where algebra, as performed in grade school, is different than algebra performed on a computer. Now, because the thing is that there are 2 ways of writing the answer. You could write 13 minus square root of 168, or equivalently 1 over 13 plus square root of 168. And now if you do the second way, which is from mathematical point of view equivalent, you end up with 1 over 25.961, which is 0.0385119, which equals the truth up to 5 digits. So even though we had 5-digit arithmetic capabilities, we rewrote this, and instead of getting something with only 2 accurate digits, we get something with 5 accurate digits. So rewriting mathematical expressions in trivial ways can have a dramatic improvement or change dramatically the quality of your arithmetic, because errors can propagate rapidly. Now, here's another example. I'm leaving the round-off error issue for a while, and now talking about the efficient way to evaluate expressions. Now, consider a polynomial, simple polynomial, with n terms. Now, how would you compute it? Well, one way to do it is to take x and then raise it to, oh, this is wrong. This should be n minus 1 exponentiations, n minus 1. You take x and then you do n minus 1, well, actually n minus 2 exponentiations, because x to the 1 is x. But you could do, so you could do a bunch of exponentiations, and then you multiply the a sub k with the x to the k, and then you add up the n terms. Okay. Now, exponentiation is expensive. That's the way it is. Now, when you have integer exponentiation, you can just replace it. Xi is just equal to the product of I x's. And so you could do that. That'd be faster than doing these various exponentiations. A better method is just compute x to the 1, and then x to the I plus 1 is x times x to the I. And so then you gather these up. You just have n multiplications instead of the n exponentiations. And so that's going to be faster. The best method is something called Horner's method, where you take an ordinary polynomial and you rearrange the term. So the intercept term is a0. But once you've taken a0 out, the rest of the polynomial is really just x times something. So you can factor out that x, and you get x. The rest of it becomes x times a1 plus blah, blah, blah. So then what that means is you have one less power of x in all these terms. Now, of course, you can repeat that. Once you've taken out a0 and a1 times x, then you have something which also is divisible by x. And so you end up with this nested sequence of additions and multiplications. So Horner's method is faster. Now, it's not that I'm telling you that you should write up all your polynomials in a Horner method fashion, but this is just an example of how small changes in how you write up the equations can have dramatic differences in terms of speed. And you just have to keep that in mind. In particular, one thing that is a killer is if you have the same expressions that appear multiple times in your overall formula. And getting rid of that is generally worth the effort. So how you write things doesn't matter in algebra, in mathematics, but it matters a great deal in terms of in computation performance. And so here's just a little table about basically the dumb direct method and then these various alternatives. Now, in numerical analysis, there are two kinds of algorithms. Now, the ones that you're familiar with from grade school, high school algebra are basically direct methods, such as the quadratic formula. You have a polynomial described by this, and then so you have an A, a B, and a C, and you just stick it into some formula, and then which amounts to having, you have to do 1, 2, 3 multiplications, then you have to do a subtraction, and then addition or subtraction, and then you have to do a multiplication and a division. It's a fixed number, finite fixed number of operations in a pre-specified sequence. That's what a direct method is. Now, when it comes to any serious problem, direct methods are not available. There's no direct method for computing general equilibrium, no direct method for doing maximum likelihood, unless you have some special problem with a closed form solution. Generally, what you have to do is an algorithm is going to compute a sequence of guesses, where the k+1 guess is going to depend on the history of the previous guesses. Hopefully, each success of x sub k is getting you closer to an acceptable approximation to the true answer. But we don't know how many steps it takes before you can stop it. Now, this is a key thing when you have finite precision arithmetic, is you have to have some criterion whereby you decide whether or not to stop or keep going. Now, if you stop soon, then, well, you have a small amount of time, but you probably also have low accuracy. Time and accuracy is a direct trade-off here, typically. The longer you let the sequence run, the higher the accuracy is, hopefully. But you don't know when to stop. If you have a prescribed target accuracy that you want, a priori, you don't know when to stop. How do you deal with that? Okay, no. Well, one way is to get acquainted with basic facts about the convergence of limits. Okay, Yasmin, you raised your hand for a while. What was the question?
It was
Yes?
Johannes who was still
Johannes,
has a
okay.
raised hand.
Okay, Johannes.
Oh, sorry, I think that's still from the beginning when we
Okay,
did
so
the try.
okay.
Yeah.
Okay, good. As I said, I will.
Johannes,
Yeah.
you can like lower your hand as well.
Yeah, well, I'm not seeing it anyway, so I'm just looking at the chat. Okay, good. Now, we have to understand the mathematical properties of convergent sequences. Now, the key concept is convergence at rate q. Now, suppose that a sequence is converging to x star. Now, what we're interested in is measuring the speed with which it is getting to x star. And one notion is you pick some number q, and you look at the error of the k+1 iterate and divide by the q power of the error of the kth iterate. So this is the error of the last iterate. This is the error of the next iterate. And you hope that if this inequality is true, that when asymptotically, this is limit. And by the way, this is limit. I'm not going to get into lim sup versus lim int things. So I'm assuming there's a limit. And so what one thing you do is you ask, well, okay, if I take the current error, if we relate the current error to the previous step's error, and if this ratio with the q power in the denominator is less than infinity, then it converges at the rate q. Now, the most common q that we aim for is 2, which basically says that if you basically says that the current error divided by the square of the previous error is less than infinity. Now, think about what that means for convergence. Suppose that the previous iterate had error of 1/10. Now, for this to be true, the error of the current iterate has to be something on the order of 1/100. Because you square 1/10 and you get 1/100, and so this inequality forces this one to be small relative to 1/100. This is quite rapid convergence. And this is what the kind of convergence that is available in Newton's method, sort of the pure Newton method. Now, more likely, in economics problems, we have what we call linear convergence. And that means that you put a 1 equals 1 for q, and so you're just looking at the ratio of last iterate's error to the current iterate's error. You're just looking at the simple ratio. Now, by the way, that ratio, asymptotic, had better be less than 1. If it's anything else, then you don't have convergence. Now, if you have this property that the errors shrink at the rate beta, so that means that the error this time is beta times the error last time, where beta is some number strictly less than 1, then you have convergence linearly at the rate beta. Now, sometimes you have algorithms where this limit actually goes to 0, and then that's called superlinear convergence. Okay, so now the question, okay, so these are just terms and definitions. Now, so whenever you have one of these iterative algorithms, you have a sequence of xk's, converges to some unknown solution, x star. Let's say you believe that it converges. Now, what is the criterion you should use to show that you are close enough to x star for your purposes? And what criterion do you have for stopping at a finite k? Hopefully the small k. You need a criterion. Now, this is not so easy. Consider this sequence. The summation of 1 over j, from j equals 1 to infinity. This sequence diverges. As you increase k, this goes off to infinity. However, it goes off to infinity very slowly. So if you take the first 1,000 terms in this sum, you only get to 7.485. So it's off to infinity, but at a very slow pace. Now, you need to come up with a stopping criterion, which will attempt to tell you if your sequence is converging at a rate which allows you to stop at some finite time, or if that's not the case. You need some criterion. Now, we call these criterion stopping rules, and by the way, they are heuristic methods in many ways. Now, here's a favorite one of economists. Stop when the sequence is not changing much. So stop when the difference between the last two guesses is small. And for some epsilon, for some small epsilon. Now, this is never a good idea. Furthermore, all you have to do is change the units of x. So instead of x being measured in pounds, you can measure it in tons. Well, that means that everything is then 2,000 times slower, a smaller number, and so the differences are going to be 2,000 times smaller. So it's easy to get convergence. Now, if you take the units out, which is what you should always do. By the way, those of you who have taken physics courses in the past understand that before you do anything, you've got to express things in a unit-free fashion, or at least keep track of the units. And so this is very useful in these contexts. Now, this simple rule can fail spectacularly. For example, if we go back to that infinite sequence, or the sum that diverges, even if we had the stopping rule of 10 to the minus 3, it would stop at k equals 1,000 at the number that we had, 7 point something, and it would say, oh, it's converged, even though we know other math tells us no, we're nowhere near the limit. The limit is infinite, and so this rule is not reliable at all. Now, here is talking, but it doesn't change much relative to 0. Okay. This is a good idea. Looking at whether or not the current iterate is small relative to the last guess. So this at least takes out the units. So this is like what is the percentage change in xk as we go from iter k to iter k plus 1? Now that's nice, but if it's trying to converge to 0, it's not going to work so well, because asymptotically xk is going to go to 0, and then you have a 0 in the denominator. Things aren't going to go well. So what you have to do is add some small delta here, and then now you're adding in implicitly some kind of units, but you make this a small number, and so then you stop if this ratio is small. That at least takes out the units. Okay, this can also fail spectacularly, and so this also is not reliable. Now, sometimes we have some other evidence. Sometimes we know, for example, if we're using a pure Newton's method, we know that the sequence of solutions or guesses will converge quadratically. So if we know that, then it's easy to come up with some rule for stopping. So for example, if in order to get, so basically the thing is that with Newton's method, quadratic convergence, if two successive iterates change or differ only by 4 significant digits, you know that you have 4 good digits. So now the quadratic convergence is unusual because the pure Newton's method is very expensive. Now, more typically, you have something like this, where you have linear convergence. For example, this is dynamic programming. You know, you have a value function, and then an infinite horizon problem, you make a guess for a value function, and you iterate. Remember, v equals tv, you're trying to find that fixed point. And so there, the iterates do converge at the rate beta, where beta is the discount factor, which is normally assumed to be less than 1. Now, if you have linear convergence, then you can construct a telescoping series, and what you know is this, is that if you have a linear convergence, then the error in the xk guess is bounded above by the change between xk and xk minus 1 divided by 1 minus beta. Now, if beta is a number like 0.9, that means that your upper bound estimate on the error is 10 times larger than the last step. So and this is even when beta is, like I said, 0.9. In dynamic programming, sometimes you want to look at a problem where it's 0.99, in which case the denominator is 0.01, and so that means that the error bound is 100 times bigger than the last change. And so this is kind of slow convergence, but at least it's a rule. Now, so you stop and you accept xk plus 1. If you have a target of epsilon, you stop and accept your most current iterate. If the change from the previous iterate is not just less than epsilon, but less than epsilon, your target accuracy, multiplied times 1 minus beta. So if beta is 0.9, this means this has to be less than epsilon divided times 0.1. So it's much tighter than any simple rule. Now, the problem is that we often don't know beta. We may be confident that convergence is linear, or at least we have some hope that it's linear, but we don't know the linear rate of convergence. So what we need to do is to, as we proceed, estimate the rate of convergence. So we're confident that there is some asymptotically some linear rate of convergence beta. We don't know what it is. So what we're going to do, we're going to estimate it. So what does that mean? Well, you see, beta is going to be related to, okay, let's look at this expression. This is, for each j here, this is xk minus j minus xk minus j plus 1. So this is one of the errors, and then this is divided by the previous iteration's errors. So looking at that ratio of the change in iteration k minus j divided by the change in the k minus j minus 1 iterate. So we know that asymptotically these ratios should be less than beta for some beta. So we don't know what the beta is. So what we do is we take we don't take all the history. We just take like the last L. We maybe have 1,000 iterations. So this L is just going to be like the last 50 or something. Because by the way, you don't want to take the entire history because the first iterations are going to be crazy and wandering around. And so you want to get rid of that history. What you're interested in, you're estimating is the asymptotic rate of linear convergence. Now, So what you do is you stop at some k, you take the L period history, compute these ratios, and then you take the max, sort of a worst case scenario thing. And then once you have that beta, if it is less than 1, then you can estimate the error to be the last change divided by 1 minus the estimated beta. Now, if beta is greater than 1, then you know you have to continue. You have to continue, you can't stop. But if that beta hat is less than 1, then you maybe feel comfortable stopping if you have this inequality, and then if you're, and use this criterion if epsilon is your target. Now, you could basically, the key idea here is that we have, this is a sequence of ratios, and we want to estimate the asymptotic ratio. Here I use basically a sup norm of the recent history. You could use other things like a p norm of the recent history. You know, it's I don't know of any theory judging between the two. The max is always a worst case scenario. Perhaps smoothing it out with a p norm is better. But at least this gets you in the game and give you some confidence in your results. Uli Dorzelski and I had a paper came out, I forget where, maybe QE probably, where we showed that in dynamic games, in dynamic games, people think, well, each firm is solving a dynamic programming problem. So they think that with solving dynamic games, you can apply the same kind of contraction mapping logic to it. Well, you can't. A game is something very different than optimization. And so what we showed is that we took a standard Pockus-McGuire model, and we showed that the convergence rates were not anything like the discount factor. It was much, much slower. But then we applied this idea to come up with a more reliable stopping rule. So this is useful in some context. Basically, the idea is that there is no foolproof way, but you just try to use the best available thing, and maybe you have to do some estimation as you iterate. Well, that's fine. Do it, and then that helps you give you a better guide to when to stop. Now, the key fact here is that whatever you're doing, there's going to be an error. You're doing maximum likelihood estimation. The point, you're not going to get the point estimate exactly right. You're going to be off on that because of some errors in the computations. If you're solving a general equilibrium model, you're not going to get the prices right and the trade and the production right. They're all the numbers are wrong. The question is whether or not the error is of economic significance. Now that requires some judgment. So then I'll give you some guidance as to that. First of all, we have to understand error bounds. Now, something is called a forward error if the error is our approximation to the solution minus x star. That's called the forward error. That's the error in the solution of the solution. Now, it's difficult to compute this, and it tends to be very conservative, but that's exactly, the definition here is forward error. Now, we typically have to do something more akin to what's, I think, generally called a back error. So, compute and verify. Now, so we have a numerical solution, let's say f of x, trying to find the x such that f of x equals 0. Now, your solution is not going to be such that f at x hat will equal 0. There will be some error. what you then do is you use the value of f at x hat or some related function to measure the importance of the error and determine whether or not we accept x hat. Compute and verify. One thing is you want to take the units out. And it's perfectly fine in your computation algorithm, you leave the units in, but then when you try to verify your answer, you got to take the units out. So basically, first compute an approximation and then verify that it is an acceptable approximation according to some economic criteria. Now, here's a math example of this. X squared minus 2 equals 0. So basically, x is the square root of 2. A 3-digit machine would give you 1.41. You plug it back into f, and you see that the error is on the order of 0.1, or 0.01. Yeah, now, who knows? That may be small, maybe big. You see, now, when you're reading numerical analysis books or math books, there's no context there. So they just tell you about limits of this or that because there's no particular context. Now, when I talk about these things, like today, it is in the context of economic models. And having that context allows you to make some judgments about what's a big error, what's a small error. Suppose that what you have is a general equilibrium model. You have a demand and a supply, and then excess demand is some function of E of P. You can think of P as a, well, here it's kind of a scalar, but the same principles go for a vector. Now, suppose that you did a numerical solution for P hat, your numerical thing. Here's your equation, and you come up with a P hat, and then you plug it into E, and it comes out to 10. Now, is that error acceptable? Well, it really depends. You see, by the way, now here we have a units problem. It depends on the magnitude of the demand and the supply. Now, if the demand is 10 to the 5th, you're talking about something so that there's maybe, I don't know, something like the monthly production of BMWs or something. I don't know. And then the excess demand is 10. Well, that's pretty good. So you're off by 10 in terms of talking about the output or the equilibrium of a market where there's 10,000 units. On the other hand, if the demand function at P hat is 10, well, then the error of 10 is not good. So it's a matter of, what is, in this case, it's what is the magnitude of the error relative to demand and supply. That's what, for simple demand and supply things, that's what you can do. So that's what you want to do. This is basically taking the units out. But this may look like a big error, but when you properly think about the units involved, it may be quite acceptable. You have to think about the context of the problem in order to decide whether or not the error is acceptable. So in general, you use some numerical method to compute what I often call a candidate solution. It's a candidate. It's a possible solution, x hat. And then you verify that x hat is acceptable approximation to the solution by computing some other, perhaps other function, g, such that g has the same zeros as f. G is now unit free, and g also represents the importance of the error. Now, in macro models, the equations that we look at often are Euler equations, margin utility of this today versus margin utility tomorrow. And so again, you can just fiddle with utils and you make those errors as small as possible. But by looking at the relative errors, the difference is then where you do this valid verification exercise. And now here, what I was implicitly doing with this demand and supply example is trying to solve excess demand equals 0. But then what I ended up computing is the ratio of supply and demand, which should be equal to 1, subtract 1, and then that gives you a relative error expression for the error. This is more what's called backwards error. Now, if your functions are well behaved, then the backwards error approach does give you a good prediction of what the forward error is. And the thing is, if you don't get supply equals demand in terms of a model, then what does it matter? If you're trying to model something like the number of BMWs demanded and sold in a year, so you're missing 10, fine. So, that's some criminal stole some, and there's in economics, none of these numbers are exact. So there's noise, and so you never would expect demand and supply to equal each other. But the question is the deviation in your solution of economic significance? I used to teach international trade when I was at a business school, and we would be talking about deficits and trade deficits and all that. And the numbers were so bad. This is in the early 80s. I doubt it's any better now. The numbers were so bad that you added up the trade numbers, and it turns out that the world was running multiple $trillion-dollar deficit. With who? Mars, Venus, Jupiter, who knows? But the world deficit was enormous. So there's noise in numbers, and you have to adjust to that, deal with that. So backward error analysis is what we've been doing. You find something. Oh no, here's four. This is official backward error and stuff. You find some other function f, which is close to the f you care about, and then this other, and then x hat is a true solution to f hat, and then you see if these two functions are close. Doing formal backward error analysis is, I haven't seen it done much in economics. When I have, it's the problem is that checking whether or not the approximate problem was close to the true problem was not done carefully. So this is true backward error analysis, but that means basically looking at another problem, f hat, which you think is close. By the way, what does close mean? If you have these two functions, what does close mean? In some contexts, you might think, well, it just means like an L2 norm or an L infinity norm. Well, in some contexts, two functions being close in L2 or L infinity is not good enough information, because you have to, in order for two functions to be really similar for the problem, it has to be similar in terms of its derivatives also. So it'd be, you have to measure it in a Sobolev norm or something. So this is backward error analysis has difficulties, and so you don't see it used much in economics. Now, here's the other thing about this whole business. We're never going to find the exact x hat that solves an equation. So that means that we end up with some criterion that x is close to x hat. Well, there's lots of numbers x hat close to any x. There's a continuum of infinity of numbers close to x. And so any of them in the small interval would be acceptable. So basically what a computer can do is give you what we would call an epsilon equilibrium. Now, the real question is, okay, so you have an epsilon equilibrium. I think the real question that should be addressed often is, how many epsilon equilibria are there? And are they different? Do they differ in any significant way from each other? And by the way, we'll be getting into things called like conditioning next Tuesday, and that puts us sort of on that trail. But the fact is that you do any computation, there's going to be an infinite number of acceptable solutions, whatever your stopping rule is. And the real question I like to ask is, how big is the set of epsilon equilibria? And if that set is not small, then you really can't. Your methods don't allow you to say much. So what you often want to do is some testing. Now, I don't know of any papers that do this, but you want to do some testing of what is a set of solutions, or a set of functions, or a set of x's that qualifies as a solution given your stopping rule. And this becomes particularly now in general equilibrium, where you have a finite number of prices. That's not so bad. But when you're doing macroeconomics, heterogeneous agent economics, and modeling, the unknowns are these functions, multidimensional functions, and I think that's a place where one seriously really should be doing this kind of analysis. How many decision rules, how many equilibrium pricing rules are acceptable equilibria according to your stopping rules? Now, by the way, this takes a lot of computing power. And perhaps that's one reason why it wasn't done in the past. However, now I think we have the power to do this. So I think now it's a reasonable requirement. Now, the other attitude here is that any economic model approximates reality. And what numerical analysis does is approximate the solution to the economic model, which itself is an approximation. Now, but that doesn't mean that because the model's an approximation that we should be sloppy. You see, you already have significant approximation problems in dealing with choosing a model to represent some economic phenomenon. I argue that in that case, that's when you want to be really accurate on your numerical solution. Now, I know the attitude is very different. People say, well, the model's kind of sloppy, so the computation can be sloppy. Well, my attitude is computation is nothing more than a lot of arithmetic. And so if I can't trust you in your arithmetic, which is just mechanical, why should I trust your views about what's a good model? Because that takes judgment, and that's a much harder problem. The computation part is easy. It's just mechanical. It's trivial if you know the math. And I often like to say, why do I like numerical methods? Well, because I'm lazy. I like good algorithms because I don't want to have to mess around and spend a lot of time watching bad stuff go. I'm lazy. I want to spend time on other things. But I also, that if somebody puts a model in front of me, I want to give them an accurate analysis of that model. Now, whether or not it's the right model, well, that's for somebody else to judge. My job is to help them analyze their models. It doesn't give me, because their models are imprecise, that doesn't give me license to then give them sloppy things. And so it's like, maybe it's garbage in, but when I send something out, I don't want the garbage to be more than necessary. So it's important to get accurate solutions. Now, my final notes here basically talk about computational complexity. Suppose you have a target error. And so how much computational effort does it take to get an accuracy of epsilon? And now some people, so the way I like to write it is that given epsilon, here's a computational effort. Or other people like to write, given a large number n of effort, what's the maximum accuracy you can guarantee? And then you get into some similar language about convergence rate and all that. Now, I find a lot of this discussion to be rather of little use. Why have a method that converges more rapidly than others? If you look carefully at what they're asserting, remember, everything here, these limits, these are all asymptotics. This is if as you want to get epsilon to 0. These are all asymptotics. And there are many times when there's some method which asymptotically is superior, but requires an enormous amount of effort to get to that low target, and you're better off using something else that isn't so good asymptotically. So this convergence rate issue is highly exaggerated. One reason is it focuses on asymptotics. And, you know, by the time we hit the asymptotic limit, we're all dead. Anyway, the world blows up, the sun is blown up, whatever. So what is the relevance of these asymptotics? They may be instructive or informative somewhat, but typically you do an asymptotic ranking of various algorithms that doesn't really tell you what you should do given your epsilon target of accuracy and your problem. So asymptotic results are not necessarily relevant. They're asymptotic. So what I always say is that you should know several algorithms for the same problem, and then see what works best for you on your problem, given your target level of accuracy. Don't let the accuracy people bother you. Let's one more comment on accuracy. Now, I'll give you an example. The simplex method for linear programming was shown to be exponentially difficult, sort of an intractable problem. By that I mean that as the size of a linear programming problem increases, the cost grows exponentially in terms of the size of the problem. Well, when people make comments like that, you have to ask, okay, they're making a quantitative comment. What is the norm they're using? And in the case of this discussion about simplex algorithm, what they're saying is that it's a worst case analysis. That if you have it if you take a look at linear programming problems of size n, and you take the problem that has the slowest performance under simplex, and you do that for each n, then yes, that will be an exponential curve. How relevant is that? Nothing. It's not relevant at all. Because then in the mid-70s, somebody pointed out that for the expected, basically an expectation, the expected time to solve linear programming problem using simplex algorithm is not exponential. It's like the fourth power of the size of the program. So yes, there's these weird linear programs that can really blow things up. But on average, simplex algorithm is only degree 4 polynomial, which is not that bad. So, you know, it's notice there are two norms being discussed in that. The complexity theory guys love, or historically love, the worst case scenario, which was very pessimistic. Now there's been a movement over the past few decades to look at average case complexity, and that can be a very different story. So this is why, you know, knowing algorithm, when somebody tells you, oh, that method is intractable, all that, you know, find out what the norm is that they're using to make that. And typically you'll find that particularly if they're just informed by the computer science literature, typically it'll be the worst case. Like Carl and I, some others work in commutative algebra trying to solve systems of polynomials. And there, even there, the case is that the typical problem is doubly exponential in complexity. Now you would think, well, we're insane to do that. Well, no, the thing is that economics problems are not typical problems. They are what we call in a small set of sparse problems. So even in the case where, yes, the average system of polynomials has double exponential difficulty of solving, thing is that the average system of polynomials has a positive or has a non-zero coefficient at every single monomial that could be in the problem. Yeah, economics problems don't have that property. They're what we call sparse. So these complexity measures are very, very misleading. And you should ignore them and move on and get things done. But you got to try things and see if they work. Now, the last point I want to make today is talking about the kinds of processes. What we're going to be talking about usually, and what most people are using, is serial processing, where there's one arithmetic operation done at a time, and you do them in a fixed sequence, and maybe then you have some branches to see, oh, what do I do here? Do I go left? Do I go right, et cetera? But it's all one thing at a time. Or now a fancy processor, you can do 2 or 3 things at a time. But that's serial processing. Now, what has been of enormous significance over the last couple decades is the development of parallel processing. And that's where you take many computers, many CPUs, many cores, whatever, and then you have an algorithm which distributes work across these, and then each of these cores do their work, and then some central manager looks at the results and then makes some decisions about what more work needs to be done. And so this is parallel processing. Now, modern chips do a little bit of parallel processing, but what really is important is the development of massively parallel processing, particularly supercomputers, and that has been very useful for me and my students. Now, I am going to talk to you in this course basically on serial algorithms. However, when it's very useful to talk about parallel processes, that's just when we do dynamic programming. I will then describe how we do dynamic programming using massively parallel architectures and what the issues are. Now, there's always political correctness kinds of things. It used to be called that you had a master processor and then it gave orders to many slave processors. So that was called a master-slave system. Well, they didn't like that terminology, so it's not. Then it was master-worker. Okay, that's a little bit more politically correct. And then, well, even master wasn't that good. So then it went to manager-worker. But then, as any Marxist will tell you, is that the manager is really a master and the workers are really slaves. So I don't understand these distinctions and terminology, but that's what there's always, this labeling is always, has to be tested by whatever the current standards are of political correctness. But massive parallelism is the way of the future. Hopefully for economics, it's what's going on in almost every other field. And this now, what I'm going to show you is some basically pretty elementary applications of parallel processing. I want to get going on some other much more sophisticated uses of parallel processing. I may mention some of those, but anyway, certainly like the dynamic programming stuff is easy to describe. Now, I think that's it for today. By the way, my habit will be that I'm going to hang around here after the official end of every lecture. So if somebody wants to just have a chat afterwards using this technology, that's fine. That's good. But before we officially end, are there any questions or comments that anybody has?
Hi, Ken. This
yes.
is Emily McGlynn.
Yes.
I'm just curious what problem you were working with when you ended up having to use like 1,000 digits, or what should we be looking for if we think that the number of digits might be the problem?
Oh, okay. Actually, next Tuesday, we'll be talking now, more precisely, it was a linear set of equations that Carl and I were trying to solve. However, what happened was that the various columns of the matrix were highly collinear. So what we're trying to think of, what we're trying to do is like regression. And if the regressors are highly collinear, you know, your estimates, your regression estimates are going to be very noisy and garbage, basically. And so that's what came up. This will be relayed next week. Be sure to remind me if I don't answer the question next week, when I'm going to be talking about conditioning and ill conditioning and condition numbers. And then if you have a problem that's ill conditioned, I'll tell you what the mathematicians will tell you, well, rewrite the problem so it's not ill conditioned. Okay, that's what they always say. But if it's ill conditioned, one way to go is higher precision arithmetic. And so that's in the problem that Carl and I did. The problem was we're trying to find a portfolio, but the returns on many of the assets were highly correlated. So the asset weights were close to indeterminate. And then with finite precision arithmetic, the computer just spits out random numbers. Okay. Any other questions? Yep.
I just raised my hand multiple times,
yes.
but it seems like you didn't see me. And
oh no,
can
okay.
I just get back to the slide?
Yeah, you should, like I said, the hand raising stuff I haven't learned. Use the chat stuff. But anyway, now, okay, or just okay. Now, what's your question?
Can I just get back to slide 23 then? You just talked about the
slide 23.
Some kind of situation where we can have this a set of right. 23.
Yeah. Okay.
Yeah. This kind of dumb questions, but I just want to have these questions. Like when we are having a set of the potential or possible solutions, and you just talked about some multiplicity procedures. Like, can you give me some kind of simple example?
Well, what I'm first pointing out is that even if the economic model, if you had infinite precision arithmetic, has only a single solution, your computations, there's a continuum of solutions that will satisfy your stopping rule, and so that the numerical error is going to generate possible multiple solutions, and that even if there's a unique x, such as f of x is 0, the thing is that when you do your iterative process to compute x, the number that comes out will depend on the stopping rule you have, and also different algorithms will come and converge to x from different directions. So you're really computing an epsilon equilibrium. When you have a stopping rule related to a target accuracy of epsilon, you're really computing an epsilon equilibrium. That's what you're really doing. And so you have a multiplicity of computer solutions. Now, the multiplicity of true solutions, that's another thing. But I'm just pointing out that even if you have a unique true solution, there's going to be a continuum of computational solutions. And you should just be aware of that, and hope that the set of epsilon equilibria is small. Actually, one thing I would like to do, one agenda I have is to push the idea that that part of the verification procedure that you use is to examine the set of x's such that it also would be accepted as a solution by your method. Okay.
Okay, thank you.
Anybody else? Okay, so like I said, I'm going to hang around for a while, available for chats, but otherwise, bye-bye, see you Tuesday.